Hello, viewers. Welcome to my YouTube channel. Students, this is my second lecture video on performance assessment of computers. I have started this lecture series on the subject of computer organization and architecture. First lecture was on evolution of modern computers. I will give a link to that video at the end of this video. So this is my second lecture video. So here we are going to see how to do performance assessment of computers. First, I will take a real life example on another product, and that will be four different airliners: Boeing 777, Boeing 747, Douglas DC, etc. The thing is that a product can be compared on different parameters. So, in this example, these four airlines have been compared on first on passenger capacity, second on cruising range, third on cruising speed, and fourth on a combined metric, passenger capacity multiplied by cruising speed, miles per hour. And as you can see that for different metric, different airliner is a winner. On passenger capacity, Boeing 747 is the winner. On cruising range, Douglas DC is the winner. On cruising speed, back is the winner. And for the fourth metric, the combined metric, passenger capacity multiplied by miles per hour, again Boeing 747 is the winner. So the same thing is applied for computer performance also. As I told you, computer is a very complex electronic machine, and it can be evaluated on different parameters, like it's how fast it can execute instruction, which is also called the response time of a computer. Second one is the throughput, which means how many jobs or transactions can be executed per unit time, or it can be evaluated on the cost of the computer, or the power consumption of a computer, or many different aspects like its form factor, how reliable it is, etc. etc. But in this course, we are going to mainly concentrate on response time and throughput. And also we will see that as the computer has many different components, instead of evaluating all of them separately or combinedly, we will be mainly focusing on the main component of the computer, and which is the central processing unit or the microprocessor. Okay, so now who measures this response time on the throughput? Like if you look at it on the perspective of a new customer for a computer, how does he know? How the customer know which computer to purchase? There are computers from Intel computers, HP computer, Dell computer, etc. Which one to buy? He's not going to buy it and then run a program and then to figure out, no, it is not that way. Okay, so for that, so is the computer vendor is finding the response time and throughput and telling it to the customer. Then how to believe on the computer vendor, because every vendor will say that their computer is the best. So for that reason, there is a third party, uh, which is a organization which is called Standard Performance Evaluation Corporation. This is a third party who has they evaluate all the computers from all vendors. So they have come up with some benchmark programs. Those benchmark programs are very long. We are going to see some definition, specification of this program. So here it is showing SPEC CPU 2006. It means in 2006 they have revised their program, um, the benchmark program, and they will be running the benchmark programs on a standard computer, and then advertise that this is the time it is taking uh, on, on the standard computer. Now, when a new computer vendor is creating their specification sheet, they are also going to run these benchmark programs in their computer, and then compare how much time it took on a standard computer, because that data is already available versus in their computer, and they have to specify a spec ratio in their specification sheet. Okay, and that is the way the customer can read the spec ratio for every vendor's computer, and they can figure out which computer is better. And it is not only for evaluating the CPU, the benchmark programs are there. Benchmark programs are there for other kind of applications also, like spec web. It is evaluating how good is a server computer. In a server, computers are not only for individual user, it is for many different users accessing the server over the internet. And then there are benchmark programs for embedded computer evaluation also. Now it is saying these benchmark programs, particularly the CPU 2006, it has 17 floating point programs written in high level programming language, C, C++, Fortran, 12 integer program. They have 3 million lines of code, etc. Usually the user programs are not that long, but because these benchmark programs are testing a computer, they are very lengthy. So in this slide, you can see some of the benchmark programs, their name, and how many lines of code it has. This number 2252 multiplied by 10 to the power 9. That means that many lines of code. Then another thing they are specifying in their standard computer, the CPI. CPI stands for cycle per instruction uh, on that standard computer. Now the CPI will change for a new vendor's computer. And then if this is the CPI and this many lines of codes are there, so if you multiply these lines of code by CPI, you get the clock cycle time, seconds, and it is given in nanosecond. Okay, this many nanosecond. Then execution time is given in no, actually this is cycles per instruction, and here it is given the clock cycle time period, clock period. So I'm going to show you some picture of the clock. What is a clock? In a computer, everything is synchronized with the clock. Clock rate and period, they are inversely related. And then execution time is number of instruction into clock cycle time, and so this will be the reference time in seconds. And now this is, if this is for a new vendors, if this is the new vendors computer CPI, they are finding this number, whereas the standard computers time was this much. So if you divide this this number with this number, you get a spec ratio, and the new vendor has to specify this in their specification sheet. Okay, so all this data is for a new computer, and standard computer has already evaluated, standard spec organization has evaluated those benchmark program on a standard computer, and they are just giving this time it has taken, and the new vendor specifications are this, and they have to come to this number and then divide, okay, like this. Now, this is a computer clock. It is generated with a quartz crystal, analog waves getting converted into digital wave, highs and low, etc. This is and everything in a computer is synchronized with the help of a clock. So this is a clock, and the high and low together is called one cycle of the clock, and this much time is called a clock period. Here several clock periods are there. So in 1 second, how many clock period, that gives you the clock rate. And clock rate and clock period are inversely related. Clock rate equal to 1 divided by clock cycle time. This clock cycle time is called the clock period. And clock cycle time equal to 1 divided by clock rate. So here one example is given. It is saying what is the clock cycle time of a processor having clock rate of 100 million hertz. Million hertz means 10 to the power 6 hertz. That means this many zeros. So clock cycle time is 1 divided by this big number, which is given in 10 nanosecond. Okay, so I am going to go through the time scale, million, what is million, how it is related to nano in my next slide. So what is the clock cycle? All the circuit in the CPU are synchronized by the clock, and speed of a computer processor or CPU is determined by the clock cycle, which is the amount of time between two pulses of an oscillator. And generally speaking, the higher number of pulses per second, the faster the computer processor. And the clock speed is measured in hertz, typically either megahertz or gigahertz. For example, 4 gigahertz means 4, after that 9 zeros. Okay, so it is the time to look at this time scale. So what is 10 to the power 15 means 10 to the power 15 means peta, 10 to the power 12 means tera, 10 to the power 9 is giga, 10 to the power 6 is mega, like that. And this we will be using this for defining the clock rate or the speed of a computer, and to telling you the clock period we will be using this unit. 10 to the power minus 6 means microhertz, 10 to the power minus 9 nano, not microsecond. 10 to the power minus 9 is nanosecond, 10 to the power minus 12 is picosecond, etc. So computers, mm, two times are evaluated. One is response time, another is throughput. Response times means how long it takes to execute a task, and throughput means total work done per unit time, task per hour or task per second. And how our response time and throughput are affected by replacing the processor with a faster version. So if your processor is faster, response time will decrease, it will take less time, and throughput will increase. And how about adding a more number of processors? So in if you add more number of processors, and then also the question is little tricky. It is not only how many processors are there, it also depends on what kind of program you are running, if the program can be run on that many processors, because usually the programs are written sequentially and they are more logical if one instruction is executed after another. And sometimes it is possible to break the program into several groups and run them parallelly, and still the meaning of the program remains the same. In such case, the throughput will increase. So, okay, so we are measuring the execution time. So as I said, computer has many components, not only the CPU, it has to access data from the memory, and then the memory has to access data from the hard disk. If we consider all components, then it will be total elapsed time. But usually we will be focusing here on the CPU time. That means how much time is taken for the CPU to execute the instruction. That way we are only looking into one component at a time. So CPU time will depend on CPU, how many CPU clock cycles are needed, and what is the clock cycle time or the clock period. Okay, this is the time it will take. And performance, we'll be talking about performance and execution time, but we must know that performance and execution time are reciprocal. More performance, higher performance means less execution time, and lower performance means higher execution time. Now that CPU time, we previously we have talked about how many clock cycles. So that will depend on how many instructions are there in a program. Then how many clock cycles, because number of cycles per instruction, and then how much time in a cycle. And you can see these parameters can be improved by different things, like instruction count depends on the program length, and instruction count also depends on the compiler, because the compiler will be translating the high level language to machine language. And then instruction set, what kind of instruction sets are there, like if you don't have multiplication in your instruction set, then you have to use addition many times. Just an example. And then organization of the computer. So you can see different parameters can be improved by improving on different things, by program or compiler or instruction set or organization or the hardware technology. CPI can be improved by either by compiler or instruction set. Clock rate can be improved by organization of the computer or the technology. So here is the first example, CPU time example. So it is saying suppose a program has 10,000 instruction, average CPI time is 4.75 cycles, and processor speed is 200 megahertz. Calculate CPU time. So clock period is inversely related to clock rate, which is 200 megahertz. So it is coming out to be clock period is 5 nanosecond. Now CPU time will be this clock period into number of cycles per instruction, which is 4.75, into number of instruction in a program, and it is coming out to be 0.2375 millisecond. Milli means 10 to the power minus 3 seconds. Let's see one other example. Okay, so relative performance. This is performance is inversely related to execution time. So it is saying the question is, if computer A runs a program in 10 seconds and computer B runs the program in 15 seconds, how much faster A than B? It's very easy. 15 divided by 10, 1.5 times. And whose performance is better? A's performance better because it is taking less time. So computer A is 1.5 times faster than computer B. Okay, improving performance. Let's look at this example. Our favorite program runs in 10 seconds on computer A, which has a 2 gigahertz clock. We are trying to help a computer designer build computer B, which will run the program in 6 seconds. The designer has determined that a substantial increase in clock rate is possible, but this increase will affect the rest of the CPU design, causing computer B to require 1.2 times as many clock cycles as computer A for this program. What clock rate we will we tell the designer to target? Okay, let's see the solved example. So computer A 2 gigahertz clock, 10 second CPU time, and computer B should run the same program in 6 seconds, but it will take 1.2 times the clock cycle. Only thing we have to know, find out its clock cycle rate, means megahertz. Sorry. Okay, so we, if we put everything here as per formula, we are getting that computer B should target for 4 gigahertz clock cycle rate. Okay, students, today it is up to this, and we will be solving more example problems in the next lecture video. Thank you for watching.